Part of her second lecture, and it is based on notes, the usual deal, dollar per note. That's how it works. Uh, it's an important opening, 7 minutes.
Okay, so we're picking up on chapter 15. I'm sorry, chapter 14. We're kind of right in the middle of it. This starts on slide 15 of that PowerPoint set if you want to follow along. At the end of the last lecture, we discussed how a galaxy like the Milky Way formed and went through the process of how you end up with a galaxy that has a halo of stars and star clusters that are moving differently and that have different ages than the stars and clusters in the disk, and how we can explain that through this kind of, various cloud collapse model into a kind of spiral galaxy that we see today. And so that brings us to a discussion about the spiral structure in the Milky Way. When we look at pictures that are obviously, these are drawings of what we think the Milky Way looks like. Again, we can't really take a picture of our galaxy from the outside because we haven't traveled that far or sent satellites that far, of course. But this is a pretty good idea of how we think the structure appears, based mainly on the distribution of hydrogen gas and also stars that we see along the disk. And from those observations, we can see that a lot of the gas and stars are collected in these regions. It's not uniform. They appear to be in the form of spiral arms, which we see as a fairly common structure for galaxies throughout the universe. But a real question is, how does the spiral structure get there? Where does the spiral structure come from? And how is it maintained? And if you look at a spiral galaxy, it kind of looks like a hurricane, so we think, just like hurricanes, the clouds are, the spiral nature of a hurricane is caused by the rotation, right? When you look at a spiral galaxy, your first impression is that it's like that because the galaxy is rotating, right? And so the rotation would force these spiral arms to appear in this kind of structure. However, the problem with rotation being the reason why spiral structure exists is that the galaxies themselves have rotated, galaxies like the Milky Way, have already rotated several times during their lifetimes based on the ages of these stars. And that would produce a galaxy where the spiral arms are extremely wound. So we call this problem the winding dilemma. Basically, that the galaxy is so old that the spiral structure should pretty much be all smeared out. So, for example, you see, this first picture here, an example of a nice spiral structure in a galaxy, but then you rotate that galaxy around another time, and if the inner part is rotating faster than the outer part, then you're going to end up with the thing getting wound up more, and by a few rotations you end up with a really weird looking spiral structure that doesn't really seem to model reality very well. So the real question is, how is the spiral structure maintaining and staying present in galaxies that are clearly rotating faster than the structure itself? And the leading theory for how the structure maintains itself is that it's not that the structure isn't rotating at the speed of the galaxy, but is rotating at a slower speed, and that essentially what we're seeing when we see these spiral arms is a density wave, right? So a density wave is a region of overdensity in the galaxy, and the wave moves through the galaxy, not the arms themselves. They can be moving, but they don't have to be moving as fast as the material. A good analogy to this, maybe this will make more sense if we think about it in terms of traffic congestion. So, for example, the cars here on the road are moving at a certain speed. Let's say they're generally moving at let's say they're going at 70 miles per hour down the road. But they come upon a barrier here that causes them to kind of bunch up because they have to slow down temporarily. So cars slow down temporarily through here and they get a lot more densely packed, but then they move past this barrier and the density decreases again and the speed picks up. So what happens here is if you look down here, you see traffic density location, you see that there's a density wave. Now the cars are, in this case, the density wave is stationary. The truck isn't moving, these cones aren't moving. So what's happening is the cars are moving through this region, right? So the cars are moving, but the density wave is actually stationary. So the place where the cars are bunched up doesn't move while the cars themselves do. And this is sort of the idea behind a spiral density wave, is that the spiral arms are caused by the compression of gas as the material orbits the galactic center. And when the material, gas and dust, hits the density wave, which can be almost stationary in the galaxy, then stars will form because of the compression of gas that occurs in this density wave. So if you look at this picture here, this is kind of a nice diagram to illustrate this. Here's a real galaxy image, and here is a sort of a cartoon version of that galaxy. And what they're showing here, you see these two arrows. There's a white arrow and a red one. The white arrow is supposed to indicate the spiral arm motion, and the red arrow actually indicates how fast the material is moving, like the gas and the dust. So if you look at this, you'll see that the red arrow is always longer than the white arrow. See how it's always a little bit longer? And that's to indicate that that stuff's moving faster than the wave itself. So gas and dust comes up and overtakes this wave. And when it hits this wave, it's already, material there. Gravity's going to cause it to slow down and compress, right? Because there's already material there. So gravity causes the material to compress. New stars form. Now those stars are still moving at the same speed as the gas and dust. So the stars that are formed will eventually move on ahead of the density wave, ahead of the spiral arm. But when you're in the arm itself, that's where you're going to see the stars as they form. So new stars will form in the arms, and then they will move past the arms later over some period of time. So the density in the stars and clusters in the disk